If a tree falls in a forest and no one's around to hear it, does it make a sound? What does this have to do with the force between two charged particles and the electric field? Keep watching to find out. In order to answer our first question, we first need to consider what happens when a tree falls in the forest. When our tree falls, it undoubtedly creates vibrations, both from the cracking of the trunk and hitting the ground. These vibrations propagate spherically away from their source. Regardless of if there's somebody there to hear it, this is going to happen. When you say sound, are you referring to the sensory perception that we have of it falling, or simply the vibrations that it creates? If the answer is the former, then clearly there needs to be a detector or somebody there to hear it. I'm going to take a stand for the sake of the analogy that I'd like to create. A tree falling in a forest does not create a sound without a detector there to perceive it. Now, what does this have to do with the forces between charges and the electric field? Last time we talked about Coulombs Law, but we didn't really talk about the whole story. To remind us of Coulombs Law, it's the law that tells us what the force is between two charged objects. It states that the magnitude of the force between two charged objects is going to be proportional to Coulomb's constant K times the product of the magnitude of the two charges, Q1 and Q2, divided by R squared, the distance between those two charges, squared. When we presented this equation, we just took it as a given. We didn't explore how the charges know that each other are there. This is what the electric field does. The electric field is how two charges can communicate to each other. When you have a charge, it creates an electric field, in the same way that our falling tree in the forest creates a vibration. Regardless of if there's an observer, the falling tree creates a vibration, and the charge creates an electric field. In order to interpret this, we need an observer. With our tree, we have a person that hears the vibrations and interprets it to be a sound. Likewise, to observe the electric field, we need a test charge or another observer. When a charge is brought near another charge, it hears the electric field and it processes this as a force. We can take this parallel a step further. When you hear a tree falling, you can determine the direction that the vibrations originate from. Imagine you're in the woods with several friends spread out by about 20 meters. At an instant, you all hear a tree fall. You all point in the direction that you heard the tree. If you could extend the directions that you were all pointing, the intersection of those lines is where the sound that you perceive originates from. You could do the same thing with small test charges. By moving a test charge around, the direction that the force it feels is going to change. Now that we have a conceptual understanding of how charges can emit electric fields and how other charges can hear them, let's talk more about how we can define the electric field and do calculations with it. The electric field is defined to be the force a charged particle feels due to the electric field divided by its charge. Now we see two interesting ways that we could rearrange this equation. If we knew that the force originated from another charge, we could plug in Coulombs Law into the equation. One of the charges will cancel, and we're left with the equation for the electric field produced by a point particle. This equation says that the electric field produced by a point particle is equal to Coulomb's constant times the charge divided by R squared times R hat. Now from this equation we see something rather interesting. If the charge is positive, the equation is positive, which means that electric field lines radiate away from positive charges. Likewise, if the charge is negative, the equation is negative, which means that the electric field lines point in towards the charge. This says that electric field lines point towards negative charges. Another way that we could rearrange this equation is to solve for the force. This is the first part of what's called the Lorentz Force Law. It says that the force on a charged particle due to an electric field is going to be equal to the electric field times its charge. I'll leave it as an exercise to you to show how Coulombs Law can be rederived from this first portion of the Lorentz Force Law and the definition of the electric field for a point particle. Now, what's interesting about the Lorentz Force Law is that it doesn't really care about what produces the electric field. I can give you any arbitrary electric field, and if I know that there's a charged particle in that electric field, we can find what the force is acting on that charged particle. In this video, we considered how charged particles talk to each other. Just like when a tree falls in a forest, it emits vibrations, charged particles will emit electric fields. With our tree, in order to perceive sound, we needed an observer to hear the vibrations. With electric fields, to perceive force, we need a charged particle in order to hear the electric field. Electric fields can be a very difficult concept to grasp. I hope this parallel helps you in understanding them.